All right. So today is day 2. We're going to talk about the day 2 content. Some of these day 2 quiz questions really related what we talked about on Monday, so I'm going to cover those first. So on Monday we talked about hyperconjugation, and that's where a p orbital that is either empty or full with one electron, so it wouldn't be full, it'll be half full. All right, you guys, go wrestle somewhere else. Empty or half full p orbital is that carbon is bonded to another carbon, and one of the sigma bonds on that carbon, it could be a CC or a CH, some sigma bond rotates into the same plane as the p orbital, and then some electron density is donated. So if it's empty or half full, more electron density would stabilize that to make it closer to a complete noble gas configuration. So if I have one carbon attached with a group, a hydrogen or another carbon sharing electrons in there, that would help stabilize it. If there's more carbons that do the same thing with hydrogens or other carbons, those sigma bonds can also donate electron density in there. So you want to be familiar with hyperconjugation and the fact that it stabilizes carbocations and free radicals by shifting electron density through space where sigma bonds rotate so they overlap with p orbitals. We know resonance involves side-by-side overlapping p orbitals. So the p orbitals are all in the exact same plane, whereas the angle here, when I have a sigma bond overlapping with a p orbital, is usually 109 or close to that. The angle here is 90 degrees. So while this is kind of pointing away from the p orbital where it's meant to overlap, so the overlap's not as good, in resonance, the overlap is excellent. So the side-by-side overlap here allows electron density to be shared. That's what creates pi bonds, and that's what stabilizes carbocations. So if I have an empty p orbital and it's a carbocation, or if I have a free radical and it has one electron, either way, the overlapping p orbitals side-by-side create large extended molecular orbitals that cover all those atoms, so the electrons can attract all the atoms at once, and I don't have these concentrated sites of instability. The instability is spread out over multiple atoms, and we know when we're dealing with resonance, the true structure is the resonance hybrid, so we have to draw all the individual contributors and then represent what the average of those looks like in the form of the hybrid. We didn't really talk about induction because induction isn't really relevant for free radicals, but it is relevant for charges. So if you recall, induction has to do usually with electronegativity differences between atoms. So for example, if I have a carbocation and maybe there's a CO double bond nearby, well, through induction, we know oxygen's more electronegative than carbon, and so oxygen attracts electrons, creating a partial positive. So in this situation, the induction would make the carbocation less stable, would make it unstable, because the partial positive here, which is due to the electronegativity difference and this cloud of electrons shifting away from the carbon, that positive would attract electrons away from this carbon and make it even more positive. So it would only destabilize the carbocation further. In contrast, if I have a carbanion, then in shifting electrons away from the carbon through induction, creating a partial positive here, attracting electrons away, a full negative of a carbanion would be stabilized by a partial positive by attracting electrons away. So induction can be destabilizing, it can be stabilizing. If I had a carbocation that were bonded to a bunch of carbons or even a silicon, which would be even lower electronegativity, a lower electronegativity atom allows electrons to shift through induction toward a positive, so that would stabilize it. So induction can involve electrons shifting away from a group or toward a group, And depending on the charges involved, that may stabilize it or destabilize it. So you want to be aware of how electronegativity differences and the resulting partial charges can affect the stability of formal charges around the area. The next quiz question that related to the content we talked about yesterday involves drawing resonance contributors and resonance hybrids. So we did a little work with that yesterday. So if I have a free radical here, I recognize it's allylic to this pi bond, but not this one. It's too far away to be in conjugation with this pi bond. So I might think about p orbitals extending over all of these atoms, creating large molecular orbitals in resonance, but really to show for sure whether or not a pi bond can be involved in resonance, I have to start drawing the contributors. So I'll push this electron in to make a pi bond there. It can join with one of these. And where can the other one go? It can't go over here. There's already a complete noble gas configuration. The only other place for it to go is onto that carbon there. So that would create this structure here, where now the free radical is at that position. And this other pi bond now is the free radical is allylic to it. It's still not allylic to the one up here, so this pi bond here can't really get involved in the resonance, but this one down here can. So if one electron moves in to form a pi bond there, another electron can join it to complete the pi bond, and the other would come out here onto that carbon. Oops, these should be resonance arrows. And that would create that resonance contributor. So at most, there are 3 resonance contributors you can draw for this. There's no way to get this pi bond involved in the resonance without creating a much less stable contributor than the 3 we have. And we know only the similarly most stable ones will really contribute to the hybrid. So when we're drawing the hybrid, it would be the average of those 3 structures. And that involves, throughout this area, a p orbital that extends over all those atoms, right? So each one of these bonds is sometimes single, sometimes double, sometimes single, etc. So each of those bonds is in reality existing as somewhere in between a double and a single in that area where the electrons are shifting around. And then I have a one free radical that's spread out over this carbon, and this carbon. So in the hybrid, I would show a partial radical specifically existing on those 3 carbons. And that's really important because when a radical forms on a carbon, what's it likely to do? It's likely to maybe abstract a halogen or a hydrogen and have a reaction occur there. So if this hybrid were reacting with a chlorine molecule or a bromine molecule or something like that, the free radical could abstract the chlorine and connect it at that position, or at this position, or at this position. So from the contributors that exist and the hybrid that results from that, I recognize there are 3 different regiochemical outcomes once this radical forms for where the next part or step in the reaction can take place. And the next quiz question was related to showing curved arrows. And I asked you to explain what was incorrect about each of these 4. So in the first one, the arrows that are drawn would indeed actually produce this product. But what we said about rearrangements with free radicals is that they don't occur. So even though this would be a correct way of showing a methyl group shifting over to the neighboring carbon, we don't really see that happening. So there's nothing wrong with the arrows necessarily, just that this reaction would not occur. So that particular movement of electrons is just not something you see with radicals. It's not terribly unreasonable, but we don't see the methyl shift. Even though it would go from a less stable secondary free radical to a more stable tertiary free radical, it's favored thermodynamically because the tertiary is more stable than the secondary, but the kinetics involved probably go through a prohibitively high transition state. So you just don't see that occurring. So don't do any methyl or hydride shifts on a free radical. You can do those on a carbocation. That happens readily and quickly, but not for a free radical. So the second one here, what's the problem? Well, the problem is this arrow is showing one electron coming in here, but I can't make a bond with only one electron. And this arrow is showing the iodine as a leaving group. It's a double-headed arrow, so it's implying the iodine leaves with both electrons. That would produce I minus, not an I radical. So the problem here is this arrow. So the R group can come in here and start bonding with this carbon, but it needs an electron from this bond. And the other electron from the bond would go to the iodine. So I need 3 arrows there. Because the 2 electrons in this bond are both going in different directions, I need a single-headed or a fishhook type arrow to show both of them moving. Similar situation down here. I can't start a double-headed arrow on a single electron. There's only one electron moving, so that arrow is not correct. It should be a single-headed arrow to show the single electron coming in. And again, I can't make a bond with only one electron. So one of the other electrons from the pi bond would have to join up with it while the other electron moves over here, and a double-headed arrow would show both electrons. If both electrons are moving over there, I'd end up with a lone pair. But since I end up with a single electron, I need a single-headed arrow to show that. And in the fourth one, this R is going to be bonded to the hydrogen. That probably should have been shown there for you. Oops. To confirm that that's forming. But again, I can't form a covalent bond or sigma bond with only one electron. So one of these electrons has to join up with the electron that the R group brings in to make that sigma bond, and the other one staying behind is correct to show that remaining free radical. Any questions about any of that? All right, so let's delve into some newer content here. So we'll pick up where we left off last time, talking about regioselectivity. So initially last time we were talking about methane. There aren't any regioselectivity issues when it comes to methane because all 4 hydrogens are equivalent. But here I've got propane. I've got 2 different types of hydrogens. Right? Due to symmetry, these 6 hydrogens on the methyl groups are equivalent, but these 2 are unique or different from the other 6 because if I replace one of these hydrogens with a bromine or a chlorine, I would get this structure. If I replace one of the 6 hydrogens on the outside, I would get this structure, right? So just to point out as well, if you imagine the X group over here replacing one of these hydrogens versus over here where it would have replaced one of these hydrogens, those 2 are the same. I just flip the molecule over like a pancake and it'll lie directly on top of that. So they're superimposable, they're not different, so I don't need to draw both of them. But they're 2 separate products here. And so we want to investigate what happens when I use chlorine or bromine and use light or heat to initiate this radical reaction we were talking about last time. How can we predict where the halogen will attach and what the major products will be? So that's what we're going to talk about in detail here in the first part of today's lecture. All right, so chlorination. If we did this reaction, the one we were just talking about with chlorine, experimentally, you would get 2 products, as we just predicted. 60% of the product would be involving the secondary chloride, and 40% would include the chloride at the primary position. So let's answer some of these questions. Which step in the mechanism determines the regioselectivity? And it's really the first propagation step. That's the step where the free radical that's created after this breaks homolytically picks off a hydrogen. So it could abstract this hydrogen, leaving a radical at the secondary position, or it could have abstracted this hydrogen, leaving an electron behind at the primary position. So why would it happen more often at the secondary position? Well, the secondary free radical is more stable than the primary one, right? There's more hyperconjugation here, more neighboring hydrogens, that can rotate their sigma bonds into the same plane as the p orbital and overlap to stabilize the incomplete noble gas configuration of the carbon. We have more of that there than in the primary position. So that's illustrated here with this energy diagram. As we said, the primary free radicals, less stable, higher in energy, which also means it's higher in free energy or less favored thermodynamically than the secondary radical, specifically due to the hyperconjugation we discussed. And that's not only true once the radical forms, it's also true during the transition state. So this is a situation where we're focusing on the kinetics. If we want to know which pathway it's going to go through, since we're not looking at the stability of the final product, which would be thermodynamics, we're focusing on the pathway that forms that product, right? Just to point out, the final product, both of these are both perfectly stable. There's really no major difference between their stabilities once we get to the final product. So it's not like we get more of this one because it's more stable in the end. That would be a thermodynamic argument. If we're comparing their final stabilities versus the initial or versus one another, that would be looking at the thermodynamics in terms of which is favored because of its enthalpy or entropy. But really what we're going to see is that this one we get more of because the pathway it goes through is different. And that's kinetics. Kinetics is about how often something occurs because it goes through a lower energy pathway versus how something else forms less often because its transition state or energy of its pathway is higher in energy. So what's happening during the transition state? So we're looking at something that's kinetically controlled. Why? Because there's an energy difference during the transition state where one happens more often because it doesn't require a strong collisions. It'll be a much more often the collisions will have the energy necessary to get to the lower energy transition state than the higher one. So what's happening in the transition state of this first step? Well, what's happening here is we've got the propane and the chlorine free radical, and so it has to pick off that hydrogen. So in the pathway where it produces the primary free radical, the transition state would look like this. The hydrogen would start breaking away and it would start to form a bond to the chlorine, right? So if you remember, when we draw transition states, we use a dotted line to show any bond breaking or forming. The chlorine started with a radical. The radical ends up on the carbon. So at the point where it's transitioning, the chlorine radical is starting to go away, so now it's only a partial radical. And the carbon radical is starting to form, so I get a partial radical there. In the other pathway where I have the same reactant, but it's the secondary hydrogen that's removed to draw that transition state, that hydrogen will start breaking its bond with the carbon and forming a bond with the chlorine. Again, we're transitioning between a radical for the chlorine and HCl, so it's only got a partial radical during the transition state, and the radical on the carbon here, the full radical intermediate, forms after the transition state, but during the transition state it's starting to form, so I have a partial radical there. So if we're looking at the transition states and we're recognizing that this one's going to happen more often because its transition state energy is lower than the other, what we're noticing is even a partial free radical, if it's in a secondary position and stabilized by hyperconjugation, is going to be more stable than a partial primary free radical because there isn't as much hyperconjugation to stabilize. So there's an energy difference for the radicals due to hyperconjugation, and there's an energy difference for the partial radicals that form during the transition state due to hyperconjugation. So let's compare that to the situation with bromine. Right, so we just looked at chlorine reacting. If we look at bromine reacting, what do we see? We see a big difference in the ratio of the two potential regiochemical outcomes. Here the reaction at the secondary position is much more favored, right? When we had chlorine, it was like a 60-40 ratio, much closer to half and half. Here, almost exclusively, I get the secondary product. I get almost none of the primary product. So it's the same step in the mechanism, the first propagation step, the step where the radical starts to form on the carbon. Right, so if we're looking at the secondary one, still the same process, except now we have bromine. It abstracts the hydrogen, leaves behind a free radical at the carbon. So during the transition state, it would be very similar. The only difference is we've got bromine here. So as the bond starts to break, the bromine starts to lose its free radical, and the carbon starts to pick up a free radical. So the question then is, why is there a difference in the regiochemical outcome here versus with the chlorine? And the answer has to do with the energy gap. Right? If one pathway is lower in energy than the other, but it's just by a small energy difference, well, yeah, there would be more often for it to go through the lower pathway, but if it's only a small energy difference, a fair amount of the collisions will probably have the energy necessary to get through the other pathway as well, and I'll form significant amounts of both radicals, and then a chlorine would end up attaching to both sites fairly often, and I would get roughly equal amounts of both. So if the bromine is much more selective and reacts almost exclusively at the secondary position, that must mean when I'm dealing with bromine, the energy gap here is bigger than the energy gap when I have chlorine. And the reason for that has to do with the Hammond postulate. So again, we're talking about kinetics. We're talking about the pathway that the reaction goes through. If it were thermodynamics, it would be a comparison between the reactants and the final product. But really what's important for the regiochemical outcome is only what's happening in the first step. The first step is what produces the free radical. Once the free radical is produced, then that's the carbon that's carrying the free radical is the carbon where either the bromine or the chlorine is going to end up connected in the final product. So that's why we're focusing on the first step. So what's going to help us explain this is the Hammond postulate, which we kind of glossed over last semester because we didn't have any good examples to illustrate its importance. I didn't want to focus a lot of time on it if there wasn't the opportunity to apply it in a way that would help you remember. But now we have that opportunity. So the Hammond postulate tells us that if two species on the same energy diagram are similar in energy, then they're also similar in structure. So what we see here is in the chlorination, because the first step is exergonic, the transition state energy is closer to the reactant energy than it is to the product energy of that step, right? So the product here is the free radical. So since the energy of the transition state is closer to the reactant than it is to the free radical, that means that the transition state will look more like the reactant than it will like the free radical, right? So what are we talking about here? The reactant is this, and the chlorine radical. The carbon free radical is the intermediate that's formed after this first step. So in this first step, the chlorine abstracts a hydrogen and produces a carbon free radical. So what we're saying here is the transition state isn't actually halfway between those two states. Because it's closer in energy to the reactant, it actually looks more like the reactant. So we drew the transition state for that. So let's just imagine we're looking at the transition state for the secondary, the abstraction of the secondary hydrogen. So what we said was a transition state involves the hydrogen breaking away and the chlorine picking that up. But to make this more accurate, now that we're thinking about the Hammond postulate, we have to recognize that because the transition state is closer in energy to the reactant, it looks more like the reactants. The chlorine hasn't really had a chance to start to bond very much with the hydrogen yet. And so it still carries almost all of the radicals, a very large partial radical there. And the hydrogen isn't really abstracted much yet because the transition state's close in energy of the reactant. It still looks like the reactant mostly, where the hydrogen's still mostly intact, and the carbon has only started to develop a very small partial radical. That's true for both the primary and the secondary. So if we looked at the secondary versus the primary, what do we see? In both of those instances, the chlorine hasn't really started to come in yet, so it's still carrying most of the radical, and the amount to which the hydrogen's been abstracted to produce a free radical here is pretty minimal, so we have a small free radical. So if the quantity of the partial free radical is very small, there isn't much of an energy difference between it being stabilized by hyperconjugation or not, right? So if I don't have any free radical at all, obviously there's no difference in stability. If I only have a tiny fraction of a free radical, there's only a small difference in energy. So what we're saying here is this energy gap is small because there's only a small partial radical that has started to form during the transition state. And so there's only a small energy difference between the one that's slightly more stable due to hyperconjugation than the other one. We can contrast that with the bromination. Because that same key step in the bromination reaction is endergonic, that means that the transition state is much closer in energy to the carbon free radical than the bromine free radical. It's much closer in energy, which means it's also much closer in structure. So when we're dealing with bromine, we don't have most of the free radical on the halogen, we have most of the free radical on the carbon because it's very close in energy and structure to the intermediate where the free radical exists on the carbon. So if we were to draw what that would look like, we would have the hydrogen already being almost completely picked off and already started to bond quite strongly with the bromine. So the bromine's remaining free radical is small, and the amount of free radical on the carbon is almost a full free radical because it's almost to the point where the free radical is fully on the carbon. And if it were at the primary position, it would be similar. The hydrogen would be almost completely gone, large partial radical, and it would be starting to really connect with the bromine, so the bromine only has a small partial radical remaining. So now there's a big difference. If it's almost a full free radical, because the partial free radical is such a large amount, there's a big difference between the hyperconjugation that stabilizes it on a secondary carbon versus not much hyperconjugation to stabilize it on a primary carbon. So now there's a bigger energy difference between those two pathways, so almost all the molecules go through the lower, significantly lower energy pathway. Right? So that's basically what's happening here. So in the chlorination, as we just said, the transition state looks more like the reactants because it's closer in energy to the reactants, and the reactants involve the free radical existing on the halogen rather than the carbon. But in the bromination, the transition state is closer in energy to the product of that step, which is the carbon free radical. And so if the transition state looks like that, it involves a very large partial radical on the carbon. And so if that's stabilized well, then it'll be way more stable than if it's on a primary carbon or something where it's not effectively stabilized. All right, so that's what we're seeing here. The bond is between the hydrogen and the carbon is only beginning to break here because it's still similar to the reactants. So I only have, this should be more dramatic, only a small partial radical, and the majority of the radical stays on the chlorine. But with the bromine, since the transition state is closer in energy and more similar to the carbon free radical, which is the product of that first step, that's where I have a very large partial free radical on the carbon and only a very small one on the bromine. And so if that radical is secondary, it's almost a full radical. So that we need the hyperconjugation to really stabilize it. And that makes it much more stable than it would be if it were on a primary carbon. So the greater the quantity of the radical, the more of an energy difference there is if that radical is well stabilized by hyperconjugation versus not well stabilized by hyperconjugation. The carbon because the bromine reaction produces such a large partial free radical on the carbon must be able to stabilize it for that pathway to be relatively low in energy. But for the chlorine, most of the free radical stays on the chlorine. And so since there's only a very small partial radical here, it doesn't really matter if it's well stabilized or not. There's only a small energy difference between the pathways. So this is what we see for the energy difference. With chlorination, the energy differences are small. So I don't get much of a selectivity. There's a big energy difference between primary, secondary, or tertiary radical, but there's only a small energy difference between primary, secondary, or tertiary partial radical. If the quantity of the partial radical is small, there's only a small energy difference between those three pathways. And so they all occur fairly often, and I get a mixture of products. The reaction won't selectively produce one product over the other because the pathways are all similar in energy, and so they all happen fairly often. But with bromination, because the transition state is so close in energy to the carbon radical, it looks like a full-on radical almost. It's a very large partial radical formed during the transition state. And if that partial radical is not stabilized by well by hyperconjugation, it's going to be much higher in energy than one that is better stabilized by hyperconjugation, or even more stabilized by even more hyperconjugation. So now I have much bigger energy gaps. And most of the reactions won't have the energy to go through these higher energy pathways, and so I'll almost exclusively get reaction at the tertiary site. This is extremely useful because if we want to do this reaction and we have some complicated structure, if there's one site on the structure that goes through a significantly lower energy pathway than the others, then bromine can be used to selectively undergo substitution at that site due to its pathway occurring much more often than the other pathways. And so that's what we see if we look at this molecule where I've got 9 primary hydrogens that could be abstracted and 1 tertiary hydrogen. And so because there's a significant difference between the reaction at the tertiary pathway versus the primary pathway, it goes through the tertiary more often. Even though there are 9 times as many chances for it to bump into one of these hydrogens on the outside, it still gives me most of the reaction at the tertiary site because the pathway is a lower energy pathway. But I still get significant quantities of both. And if I have both, and I only want one, then I have to remove the other by chromatography or some other technique to selectively purify this substance and remove the other one. But since in the bromine situation, the tertiary pathway is much lower in energy than the primary pathway, almost none of the reactions will go through that pathway, and I can get almost exclusively all of my product formed from the lower energy pathway where it goes through a tertiary free radical, and then the bromine connects to that free radical to finish the product. So it's thousands of times more often occurring at that site than the other site because the pathway is significantly lower in energy due to the hyperconjugation stabilizing the large partial radical that forms here versus the large partial radical that would form at the primary site. So here's a table that shows the relative rates of reactivity for primary, secondary, and tertiary sites depending on the halogen that's used. And what we see here is the least regioselective is the fluorine. There's almost no difference in the energies for those 3 pathways. And why is that? Because when the fluorine reacts, the first step is even more exergonic. In the fluorine, what we would see is the first step has very little activation energy, and then it produces the carbon radical. So in this case, the transition state is so similar to the reactant that almost no radical even forms on the carbon yet. And so whether the carbon's primary, secondary, or tertiary, it doesn't matter if the quantity of radical that's formed there is almost nothing. So there's almost no energy difference between the tertiary versus the secondary versus the primary pathways. There's a difference in energy once the radicals formed on the carbon due to hyperconjugation, but during the pathway there's almost no difference. So there's a slight difference, but it's not much. And that's why when fluorine is involved, it's not very synthetically useful because there's no way to really selectively install a fluorine by substituting for a specific hydrogen in a controlled way. And what we see with bromine is a lot of selectivity. The primary pathway is very slow compared to the secondary pathway, and especially compared to the tertiary pathway. So when there's a big energy difference in the pathways, you can selectively control at which site the bromine will end up forming a radical and then end up being connected. And so we see here from this table is a general trend where we can say the more reactive, the less selective. The more reactive it is, the less selective it is, because there's not much of an energy difference between the transition states when they all look so much like the reactants. Any questions about regioselectivity for these halogenation reactions? All right, let's take a look at stereoselectivity. So imagine you had butane. Here we got butane, and we're going to use chlorine. We're going to do this reaction. As we just said, we would get a mixture of chlorine reacting at the secondary position as well as the primary position because these two pathways are similar in energy. Okay, I'm seeing a quiz question. They're more reactive because they're more unstable as free radicals, right? Yeah, the halogens, right. The halogen, yeah, the fluorine as a halogen is more reactive than the chlorine and then the bromine because as a free radical, it's more unstable. It starts much higher in energy. That's right. And since it starts higher in energy, it's similar in energy to the transition state, so there also isn't much of a difference in energy between the different pathway transition states as well. That's right. That's correct. Nice job. All right, so if the chlorine reacts with butane, I get these two regiochemical outcomes. In terms of this product here, obviously if I draw the chlorine with a solid wedge versus with a dashed wedge, there's no difference between those two structures, right? Because this bond here can freely rotate. And if the chlorine's pointing out at me, if the bond rotates, I can make it point behind, and those two structures are exactly equivalent because they're superimposable upon one another. So when there's no chiral center, there's no stereochemical issue at hand. It doesn't matter which side the chlorine connects on, whether it comes in from the back or from the front, because the rotation makes those two structures that would result identical to one another. But if the hydrogen here is removed, it could be the one that was initially connected with a solid wedge or with a dash wedge, doesn't matter which. If that's removed and a free radical is produced, we can think of that free radical as being in a p orbital, which has equal quantities of electron density both above and below those two lobes. So then when the chlorine comes in to put that chlorine on there, it could come in and overlap with the top lobe or the bottom lobe. And so that's why I get a racemic mixture. Because this free radical behaves as if it's flat and the electron density above and below the plane is equal, there's equal probability for the fluorine to come in from the top. Oops, like that. From the top, which would give this product. There's equal probability of that occurring just as much as there is chlorine coming from the bottom, which would give the dashed wedge a connection. So these two molecules are enantiomers. They're not superimposable, but they are mirror images. And so if I get a 50-50 mixture of those, that's a racemic mixture. So if you don't remember what the term racemic mixture means, it means you have a mixture, 50-50 mixture of two enantiomers. In this specific case, you would get equal quantities because there's no sterics or other reason why the chlorine would necessarily come in on the top more often than the bottom, or vice versa, so I get equal amounts of both of those. So what steps were responsible for the stereochemical outcome? That's the second step of the propagation in this reaction, right? That's this step here. Once the carbon free radical is formed, it will pick up a halogen. And because in this particular molecule it's flat, it can pick up the halogen from the top or from the bottom. I get both those products formed in equal amounts. We did say that the free radical can be thought of as existing in a p orbital or in a rapidly interconverting sp3 orbital. Either way, there's just as much electron density on top as there is on the bottom. So when the new chlorine comes in, it can come in on the top or on the bottom with equal probability, which would potentially give two enantiomers if the resulting structures are chiral at that center. If you think of it as a p orbital, that also works because a p orbital has equal amounts of electron density on both the top and the bottom. So there's equal probability that the chlorine could come in from the top or from the bottom. And that's true for any halogen. Once the carbon forms a free radical, the halogen can come on either side spatially to form a new bond between whatever halogen you have and that carbon atom. So as we said, chlorine, though, is not very regioselective because the primary versus secondary positions are similar in reactivity because during the transition state when the free radical forms on the carbon, it's only a minor partial free radical that forms. There's not much of a difference in energy between when it forms on the secondary or the primary position. So I would get some of this product. I would get some of both of these, which form a racemic mixture because they're enantiomers of one another. And so that's going to be a little bit of a mess. It's not that synthetically useful. I want a situation where I can get as few products as possible in a controlled way whenever possible. So what would the mono-substituted products look like if I had 2-methylbutane? So let's take a look at that. Butane, 4 carbons, 2-methyl. I could put a methyl here. So if I put it with a solid wedge or a dash wedge, it doesn't really matter in this case because this is not a chiral center. I've got 2 identical methyl groups. So I don't have any chiral centers here. But now, since I'm dealing with, well, let's say we had chlorination with light or heat, the chlorine could replace any one of the primary hydrogens or the tertiary one or the secondary one here or the primary one there. So I would get a variety of products. These 2 methyl groups are equivalent rotationally. So replacing any one of those 6 hydrogens with the chlorine would give me the same product. So I can draw that one time. The chlorine could also come in on the tertiary position. If it does, it could come in from behind, or it could come in from the front. Because if this hydrogen here is abstracted and a free radical forms, it's no longer, well, it's not a chiral center. And it has the equivalence of being flat, so the chlorine can come from the top or from the bottom. That creates a chiral center, though. Oh, wait, no, it doesn't, because these 2 methyl groups are still identical. Sorry, my bad. Got a little confused about that one. So this one I wouldn't draw because it's identical to the other one. There's no chiral center here. So these 2 would be equivalent, spatially equivalent through rotation. So there's 2 possible products there that could result. This hydrogen could also be abstracted, and so I get a different regiochemical outcome there. Now that actually does create a chiral center. So if the chlorine replaces the hydrogen that had the solid wedge, or if it replaces the hydrogen that had the dash wedge, now this is a chiral center. There's 4 unique groups attached there, and when 2 structures have are stereoisomers because they're identical in every way except the spatial positioning of a group. If there's only one chiral center and they have the opposite configurations at that center, that makes them enantiomers. So that would produce two more potential products from replacing the hydrogen at that carbon. And then finally, if I replace the hydrogen with the chlorine, I'd get another product. So you can see even this molecule isn't even that complicated. But once I start to get even slightly complicated, the mixture of products I would make by reacting with chlorine is very complex. So this would probably be the major product, because the tertiary pathway is going to be happening more often than the primary or secondary pathways, but not by a lot when I'm dealing with chlorine. If I were dealing with bromine, so imagine each one of these chlorines now is a bromine. Now I'm in good shape, because as we said, the pathway for bromine that goes through the tertiary free radical is going to be much more stable than a primary free radical or even a secondary free radical. So these ones are probably all now minor enough that they wouldn't form in significant amounts, and I can get, really in this case, one product to form pretty selectively, that if I want to form that, then I can carry it through to another step in the synthesis and do a variety of other reactions like their substitution and elimination and things like that. And so that's basically what we're talking about here. Here there's a slight difference though. Again, if we're using bromine, the point of that is its regioselectivity. If I only have one tertiary center, one center that will go through a significantly lower energy pathway than the other primary and secondary sites, I can expect the reaction to occur there. If it occurs there, it creates a chiral center. So we expect sometimes for the bromine to come in from the front, pushing the methyl group back, plus the opposite enantiomer that I would also get where the bromine has a dash wedge and the methyl group has a solid wedge. So that would produce a racemic mixture in equal quantities. So what's the name of that product then? If we wanted to name it, we would find the longest chain of carbons and number it from the side that gives the substituents the lowest numbers possible. So a 6-carbon chain is hexane. I've got a methyl on 3 and a bromo on 3, so 3 bromo, 3 methyl, hexane. And then to complete the name, if there is a chiral center, I need to determine if it's R or S and put that at the front of the name. So I'd prioritize the groups. The bromine has a higher atomic number than carbon. That's priority 1. This carbon with more carbons attached versus hydrogens would be 2. This would be 3. And since this carbon has all hydrogens attached to it and no other carbons, it'd be the 4th priority group. When the 4th priority group is pointing away, I make a circle from 1 to 2 to 3. And when the 4th priority group is pointing away, if it goes counterclockwise, that ends up being S. So this is the S. But since this goes through an intermediate that is flat, and that free radical can be thought of as having equal electron density on the top and the bottom, there's no reason why the bromine would have to come in from the top and end up with the solid wedge. Half the molecules would also have the bromine with the dash wedge and the methyl with the solid wedge, and so those would have the opposite configuration. So I'd have the R and the S in equal amounts. That would give a racemic mixture. Here's another example. This one's a little bit more complicated. So here there are 2 tertiary sites. So the bromine is selective. It'll go through the lowest energy pathway, which means tertiary is going to be more stable than secondary, more stable than primary due to the hyperconjugation that can occur. But if I've got 2 different sites that are both tertiary, I can't control which site the bromine reacts more often. So that would produce a mixture of products. So if the bromine comes in here, it could come in from the front, pushing this other methyl group back, or it could come in from the back, pushing the other methyl group forward. Does that make a difference? In this case, no, because this is not a chiral center. So this bond here can rotate if I just rotate the bond, it would create a rotational conformer where now the bromine has a dashed wedge and the methyl group has a solid wedge. So these are the same structure. If the only difference between them involves a rotation of a single bond, they're not different. I don't need to draw both of them. It's not a racemic mixture. I don't have a chiral center that's formed there. So that would be one product that would form if this tertiary center and the hydrogen that's there were abstracted to create a radical, and then the radical picked up a bromine. But there's also another tertiary center, as we said. And putting the bromine there would push this isopropic group back. Again, this is not a chiral center because this pathway around is the same as the other pathway around. I don't have 4 unique groups attached to that carbon. So if I take that structure and flip it over like a pancake, it would look like this. So these two structures, again, are identical. They're not different because there's no chiral center. So I don't need to draw both of them. So here I would get 2 major products. And maybe there's enough of a difference between them where I could separate them by recrystallization, or probably more likely by chromatography or something like that, if I needed one versus the other. So these two structures don't actually have any stereoisomers. So here was the next quiz question related to this same topic. So now that we know bromine is regioselective, we want to look for the most likely site for the bromine to connect on the structure. Whichever site will form the most stable free radical intermediate, that pathway will happen more often, and that's where the bromine will end up connected. So what I see here are a bunch of primary carbons, and those won't form stable free radicals, so I know the reaction is not going to occur at any of those sites. I've got 2 quaternary carbons, carbons that are already bonded to 4 things. So these 2 sites don't have any hydrogens to abstract, so I can't form a free radical there. I've got more primary sites, which won't stabilize a free radical very well. I've got some secondary sites, which would be better, but this here is where the regioselectivity is actually going to be most likely resulting in the reaction. So it's the hydrogen here. What's going to happen first, the Br2 is going to break apart homolytically due to the energy of the light hitting that bond, providing the energy necessary to break it. That's going to produce some bromine radicals, and the bromine radical is going to abstract this hydrogen. It's going to happen there way more often than the other sites because we saw there's a big energy difference between the tertiary, secondary, and primary pathway when bromine is the halogen that you're using. So that's going to produce this intermediate, where now I have a free radical here, right? This electron staying behind. And so what that does is it creates this, turns this carbon into an sp2 hybridized carbon. And I can think of that radical as being in a p orbital. So now this area is flat. And so the next bromine molecule that collides here, it could allow bromine to be abstracted from the top part of that electron density or from the bottom. And so that's going to give me 2 potential stereochemical products. So there's really only one regiochemical outcome because there's only one tertiary site versus all the other sites being less likely to stabilize or form a free radical. But in terms of the stereochemistry, if the bromine comes in from the top, it will end up here, and the methyl group would be pushed down. If the bromine comes in from the bottom, it will end up in the equatorial position, pushing the methyl group up. So since this is flat, you might be thinking, well, it's equally likely to do both. But that's not quite correct, because if it comes in from the top and ends up here, it's a smaller group than the methyl group. The methyl group's more sterically hindering. If the bromine comes in from the bottom as a smaller group, pushing the more sterically hindered methyl group up, that's not as good. As that's occurring, it's going to be a higher energy pathway, because the other methyl group in the axial position is going to start to create steric hindrance, and the repulsion of their electron clouds overlapping will make that a higher energy pathway, so it won't happen as often as the pathway that produces this product. So this product is favored thermodynamically because it's more stable with less steric hindrance, because the smaller bromine won't crowd out the methyl group that's already in an axial position as much. And it's favored kinetically because it'll happen through a lower energy transition state when there's less crowding during the electron movement. So this would be the major product that you're looking for here, and this one you could include as a minor product, or you didn't really have to draw it since it's just asking for the major product. All right, so the next section that we're going to talk about involves allylic hydrogen abstraction and a reaction at an allylic site. So what we're saying so far today is, if you have a hydrogen at a tertiary position, the bromine is going to selectively react there, because the tertiary partial free radical that forms during the transition state forms a lot more often than a primary one. But what's more stabilizing than hyperconjugation at a tertiary site is resonance. So if there's an alkene somewhere in the structure and we do the same thing, what's most likely going to happen here, especially when we look at the amount of energies necessary to break these bonds, the transition state required to break this bond, or the energy required, is significantly less. It's even less than it would be at the tertiary site, because resonance is more stabilizing than hyperconjugation. So in this case, if I have a bromine radical, it would be much more likely to abstract, even if maybe one of these other positions over here were a tertiary position and had more hyperconjugation, it would still not as be likely to react as an allylic position, a position that is going to result in a free radical that's stabilized through resonance. And so the stabilization of that free radical through resonance would mean that it's much more stable to have only a partial free radical at a couple sites rather than a full free radical, even if it's tertiary and well stabilized by hyperconjugation. So if you have an alkene in your structure, typically that's what you see. The allylic hydrogen is abstracted to produce a resonance stabilized free radical. So you might imagine to accomplish that transition, if you want to replace a hydrogen with a bromine, we don't have to worry about replacing these other hydrogens because they're not allylic and they won't produce a resonance stabilized free radical. So if you add bromine and lighter heat, you would expect this reaction to occur. The problem with this set of reagents specifically is that it also would react with the pi bond. So if you recall, if you have a pi bond and you react to bromine, last semester we did this reaction. We used carbon tetrachloride and we did it in the dark. If you do it in the dark, you don't have the light, and if you don't heat it up, you don't have the heat to form the free radicals. So the bromine reacts as a molecule, and that reaction involved a lone pair attacking while the pi electrons attack and losing this bromine as a leaving group, and we produced a bromonium ion. And then the bromine that left here is a Br minus. It's a great nucleophile, and so it can come in and attack and open that three-membered ring up and that would give me this. It would be an anti-addition, because if this three-membered ring forms with a solid wedge, the bromine has to attack from behind, and it would end up with a dashed wedge. And so that reaction works well. If you want to add two bromines across a pi bond, you can do that by adding Br2 in the dark. But if your goal is to do a substitution for a hydrogen rather than an addition across a pi bond, you want to use light, because the light or heat will break up the bromine to form free radicals, and you'll do this free radical reaction that we just talked about. The problem is, even when you use light, it doesn't instantly break up all the bromine molecules, right? So when the bromine molecules break up homolytically to produce the radicals are much less stable. So this reaction really favors the reactant side a lot. Almost all of the bromine atoms remain in the form of the molecules. Only a few will form radicals, and those radicals will start to react. But if most of the molecules are in the form of the molecule, then this reaction will also occur, and I'll have this product formed along with the one I'm trying to make. So if I'm trying to form this product, I do it in the dark, I have no problem. If I'm trying to form this product, I really can't with this set of conditions, because adding Br2 will produce some radicals. I'll be able to get some of this product, but most of the Br2 molecules remain intact, and they might react across the pi bond through this mechanism, giving me the other product. So I get a mixture of products, which is not what I want, obviously, if I'm trying to produce this product selectively. So an alternative to using Br2 and light, if I want to replace an allylic hydrogen with a bromine, instead of using Br2, because it might also add across the pi bond directly, I can use NBS, which is N-bromosuccinimide. This is the structure of NBS, and it produces bromine free radicals. So instead of using Br2 and using the light to break that sigma bond homolytically to produce bromine free radicals, if I have an NBr, those nitrogen and bromine have very similar electronegativities. The light energy can hit that. That can break homolytically and produce a couple free radicals as well. And since that produces a bromine free radical, if I do have that structure, I don't really have much Br2. Once the bromine free radicals form, if a couple of those meet up, they will couple to produce a little bit of Br2. So I might have a very small amount of side reaction, probably a minuscule amount, where the Br2 adds across the pi bond. But since I'm not adding Br2 directly in some large quantity like I would if this set of conditions were used, I just have the Br2, I just have the Br radical mostly. That would be very likely to do the hydrogen abstraction, produce a carbon radical, and then the carbon radical could pick up a Br and give me the desired product. So the idea here is NBS hit with light, producing these radicals. This radical is stabilized through resonance. The radical can undergo this shift to share the radical instability over three atoms, the nitrogen and both oxygens, which really helps to stabilize it. And the bromine radical then can do the hydrogen abstraction. All right, so here's the mechanism that we were just talking about. The bromine radical that forms as the NBS breaks up, picks off the hydrogen, produces a carbon radical. Then that carbon radical can pick up a bromine from the small amount of Br2 that forms when two Brs couple together. And since I have a very small concentration of Br2 that's present, I don't have to worry about a significant reaction between the Br2 and the pi bond occurring, giving me different sets of products. So where does the Br2 come from? It comes from the coupling of the bromine radicals that form. It's minimal, so the competing addition reaction across the pi bond is minimized. Once the succinimide radical is formed, right, so we said this homolytic cleavage produces these two radicals, and this one's stabilized by resonance. It's still a radical, though, and it still doesn't have a complete noble gas configuration for the nitrogen. So what will happen to that radical is it will usually end up picking off a hydrogen and creating more bromide radical. So when this nitrogen picks up that hydrogen, does a hydrogen abstraction. That produces a very stable product. And it also reproduces some bromine radical. And then that bromine radical can then start another set of propagation steps. The propagation also produces bromine radicals. So there's a fairly small but constant concentration of bromine radicals that can allow these propagation steps to occur. And if one gets coupled together or picked up by something, a little bit of extra bromine radicals will form anytime this succinimide radical abstracts a hydrogen off of the HBr. Where does the HBr come from? It comes from this step, right? So when the bromine radical abstracts a hydrogen, it produces HBr. So every reaction that occurs produces an HBr, so the concentration of HBr grows and gets high enough to where these collisions are likely to occur, and the nitrogen can pick up that hydrogen. There's also some potential termination steps, but they're pretty rare. Right? So termination steps usually involve coupling. Any radical that forms, the bromine could couple back together with the succinimide radical. The bromine could couple together with the carbon radical. A carbon radical could couple with another carbon radical, though that would be very rare because those radicals are very low in concentration. Usually, they just collide with the first thing they come in contact with, which is usually a Br2. So any of those radicals could couple together, and that would be a termination step. But as we said, the radicals are low in concentration, so they don't couple very often. Those steps are rare compared to how often the two propagation steps occur in the mechanism. So the vast majority of the product is produced through propagation. That's a mistake that I see students making a lot on the exam. So take note of that now if you can. If I ask you to draw the mechanism for one of these halogenation reactions where a hydrogen is replaced with a halogen, you really, unless I specifically ask, you don't need to draw any termination steps because the vast majority of the product occurs strictly through these propagation steps. You want to get into the habit of drawing your mechanisms mostly focused on the propagation steps. All right, here's another example where we're doing a similar thing. So we're using NBS specifically because we don't want BRs adding across the pi bond. So if we want to draw the mechanism here, we would start with the NBS. And the light would have to be used with a certain frequency or energy that has enough energy to break this sigma bond to produce a bromine radical and a nitrogen radical there, succinimide radical. The bromine radical would pick off this hydrogen selectively. So regioselectively, this is definitely the only hydrogen that would be picked off. The vinyl hydrogens would produce a vinyl radical, which we said last time and explained was extremely unstable. The other hydrogens at primary positions would also produce a primary radical that's unstable. So this abstraction of this hydrogen is favored for a couple reasons. One, because it produces a tertiary free radical that's stabilized by a Allylic hyperconjugation, but also when the bromine and the hydrogen come together get HBr, and when the radical stays behind, not only is it at a tertiary position, but it also is stabilized through resonance. And it's really important to recognize that resonance, because if you don't, you won't necessarily be able to predict the products that are produced. if you just memorize that the allylic hydrogen is replaced with the bromine, then you could probably predict the production of this product. But understanding the mechanism is important to predicting the full outcome of the reaction, because once the bromine abstracts as hydrogen and an electron stays behind here, it's immediately stabilized by resonance. So really neither of these exists. What exists is the resonance hybrid, where there's a partial radical at both of these locations. So either of those locations could then pick up a bromine. If this location picks up a bromine or abstracts a bromine, you get that product. If this location abstracts a bromine, then you get that product. And so you would get multiple products here, and that's important to recognize. It's a downside of the reaction, but once the free radical forms, if it's in resonance, any of the positions that carry a partial free radical could be a position that abstracts the bromine and connects a bromine to that site. If we were asking you which product might be more major, that would be difficult to predict. This product would be favored thermodynamically because the pi bond is more substitute with carbons. If you remember, we talked about that last semester. The more carbons versus hydrogens there are attached to the sp2 hybridized carbons of the pi bond, the more stable it is. But in the resonance hybrid, since the tertiary radical is more stable than the primary, this might have a larger partial radical than this, and in the transition state where this radical starts to connect, that transition state might be more stable. So that pathway that produces this structure might be favored. So this one's going to be kinetically favored. And this one here is going to be thermodynamically. So which ones do you get more of might be determined by the temperature. If you increase the temperature, you might produce an equilibrium that gives more of the thermodynamically favored product. At the lower temperatures, it might only go through the pathway that produces the kinetically favored product. So now that we've talked about that, we can explain the last quiz question. And this involves NBS. So we would start with the NBS. And the light, HV is abbreviation for light. That would break this homolytically, and we would produce some bromine radicals. So we don't have Br2 in a high concentration, so we don't have to worry about Brs adding across there, but we want to find an allylic position because we want to pick off the allylic hydrogen to leave behind a resonance stabilized free radical. So there are actually two allylic positions here. If a hydrogen were picked off of this one, I would produce a free radical at a primary site, and it would be stabilized through resonance with the secondary site. So a primary and a secondary to stabilize that free radical. If this hydrogen here were abstracted, then the radical exists on a secondary site, and the resonance stabilization would share it with another secondary site. So two secondary free radicals or free radicals shared over two secondary sites is going to be more stable than if the primary one's involved. So this would probably be the major pathway if we're just looking for the major product. So that would produce a free radical here, which will be in resonance with this pi bond. And we can imagine the pi bond breaking and one electron staying behind here. So the other resonance contributor. And once you create a resonance, or once you create a free radical that you know can be stabilized by resonance, you want to drop all the resonance contributors. Because once I rearrange these electrons and recognize that the free radical is shared between this secondary carbon and this one, I have to understand that the small amount of bromine in the form of Br2 that forms when a couple bromines couple together could react at either one of those sites. So the radical could pick up a bromine at this site, and if it did so, it would probably put it into the equatorial position because it would be less steric hindrance. So that would produce this product here. But the radical doesn't just exist there simultaneously, it also exists over here in part. So it could pick up a bromine from that position as well, which would give a different regiochemical outcome. Where now the pi bond's over here, and the bromine again in an equatorial position would avoid some sterics. So those are two likely products that would result. You might get also some bromine in the axial position, but that would probably be avoided for the most part due to the extra steric hindrance that would occur both during the transition state and when that product forms. Any questions about that? So most of the exam questions I ask about day 2 are going to come from the material we just talked about, either reacting with NBS or Br2, and the thermodynamic and kinetic issues involved with the selectivity there. But you may also see a question about some of these other radical processes or radical reactions that also occur. And one of those affects the ozone layer in the atmosphere. And so you should be at least aware of this. So you may know that ozone is O3, and the structure of ozone looks like this. There's resonance there. It's a formal negative, formal positive, but there's another resonance contributor. So really, the true structure is going to have half of a negative on the two outside oxygens. That negative is spread out evenly over both those oxygens. But that's pretty unstable because of the formal charges that exist. And so when even some relatively low energy UV radiation, which can be harmful to people, hits these molecules, it causes them to break up. So it's a protective layer. So the O3, one of the oxygens breaks off and produces this incomplete noble gas configuration, which is especially unstable. So this is higher in energy than the ozone, and that's why the light energy from the sun provides the energy necessary to do that reaction. But then those couple back together and reproduce the ozone. So it's a cycle. The ozone breaks apart, it comes back together. As long as it remains undisturbed, there should be a constant concentration of protective ozone to absorb that light. But if other free radicals are present in that layer of the atmosphere, those other free radicals, whether they be carbon radicals or chlorine radicals, they can start bonding with this oxygen. And if they bond with it, it can't come back together with O2 and replenish the amount of ozone in the atmosphere. And we need that ozone to protect us from that light, to keep absorbing that light and then keep being regenerated to create this continual cycle. So humans have been causing a depletion of the ozone layer. I think in recent years, it's started to kind of heal itself because we've really cut down on the amount of radicals that we allow to reach the upper atmosphere now that we understand this problem in more detail. But anytime humans create molecules and put those into the environment that are stable enough to reach the upper atmosphere where we need ozone to exist, but also then can form free radicals in the atmosphere and start to interfere with the regeneration of the ozone by picking up these oxygens and reacting by coupling with them. That's going to cause continual depletion of the ozone layer, which is a major problem that we need to keep under control. So these chlorofluorocarbons, or CFCs, which involve both chlorine, fluorine, and carbon, are really not good. They're stable enough and low in molar mass enough that they are a gas and they go up into the atmosphere when they're released in the environment. And then they can absorb light and break open, and then these radicals can start coupling with oxygen and depleting the amount of O3 regeneration that should naturally occur in the atmosphere. So while ozone, just to point out, is really important in the upper atmosphere to protect us, if it happens near the Earth's surface, it is a reactive structure due to its formal charge, and it is hazardous to humans to breathe in. So while it protects us when it's in the upper atmosphere, it's a pollutant, a toxic pollutant that if it occurs near the Earth's surface. It does occur as a byproduct in some industrial processes, so that's also an issue. Industries have to make sure they don't release much ozone near the surface of the Earth because it's poisonous and toxic. So instead of CFCs, which go into the upper atmosphere, create free radicals, and mess up the ozone cycle, hydrochlorofluorocarbons are a different substitute. And hydrofluorocarbons, the hydrochlorofluorocarbons, they are unstable enough where they generally decompose to produce radicals before they reach the upper atmosphere. So they don't interfere with the ozone because they form radicals and then subsequently react before reaching the ozone layer. So those are good substitutes for CFCs. Other substitutes for CFCs are these hydrofluorocarbons. They don't produce the chlorine radicals that interfere with the ozone cycle. So they're stable enough that they don't break up to create these radicals that would then react with oxygen, preventing the ozone cycle from continuing. So that's just mostly informational, but you want to be generally aware of these ideas. It's possible on an exam you might have a question, more of a conceptual question that asks you about ozone, the ozone cycle, and especially about these two key points and how we don't want molecules that have both of these features. So either they're so stable that they don't break up to produce radicals, or it'd be better if they were especially unstable, so when they do produce radicals, they produce them right away rather than going up to the ozone layer and messing around with that cycle. So that's another topic you want to be aware of. Another kind of minor topic, but one you might have a question about, involves firefighting and combustion. So if you're not aware, a combustion reaction involves a carbon fuel, carbon-carbon bonds, and carbon-hydrogen bonds. And those bonds break along with oxygen from the atmosphere breaking. When those bonds break homolytically, you get a bunch of radicals. And then when the free radicals rejoin, you form water and you form carbon dioxide. And that's combustion, right? We know combustion releases energy. It's exothermic. Why is it exothermic? Because the OH bonds and CO double bonds that are occurring in water and CO2 are much more stable than the initial bonds, especially the O2. Right? So we're starting with less stable bonds. If we look at the potential energy, we're producing more stable bonds. So we have to put energy in to break the initial bonds, but then when the new bonds form, energy is released. So on net, it releases energy that can be used to heat your home or drive your car. Obviously, our economy in large part revolves around combustion reactions. And obviously, if you have a combustion reaction, because it's exothermic and it releases energy, that energy can then go back into providing the activation energy necessary to start another combustion reaction. Right? So if you have a fire going on and there's still fuel and oxygen around, it can just continue to burn indefinitely. If your house starts on fire, you don't want it to burn down. You want to be able to stop it. So in terms of firefighting, if we want to fight a fire with chemicals, there are a few different ways we can do that. And so that's what this next section is about, using specific chemicals to prevent combustion from going out of control. So we all know if we throw water on a fire, most of the time that works. It won't work on a grease fire. It'll only spread the fire, so you want to definitely make sure you don't do that. But what water does generally is it absorbs energy, right? So when I have water as a liquid, there are a bunch of hydrogen bonds between the water molecules. And so if instead of energy going into provide the activation energy necessary to do a combustion reaction, if the energy goes into evaporating the water, breaking the intermolecular attractions, the hydrogen bonds between water molecules, then there's not as much energy available to act as activation energy for the combustion reaction. So the combustion reaction slows down. So obviously we know we can fight fire with water, but that only fights it in one way, by absorbing energy. And if the fire is out of control and it's extremely hot, throwing a little water on it is not going to stop it. It's not going to absorb enough energy to take away all the activation energy needed to continue a combustion reaction. Argon and CO2 are sometimes used in fire extinguishers, and they basically deprive the fire of oxygen. Right? So if CO2 and argon are both more dense than air, so if you have a fire extinguisher and you aim these gases at the bottom of the fire, for the most part, they won't just like lift up and float away very easily, because they're a little bit more dense than air. So they kind of smother the fire and prevent oxygen from getting around at high enough concentrations to react with the carbon fuel, and that can also stop the fire. And halons are used. So these are organic compounds that are used in some fire extinguishers, and they suppress a fire in 3 different ways. So specifically, they act in the same way that carbon dioxide and argon do, to push out the oxygen, and they're relatively dense, so they kind of hover there by the fire and prevent oxygen from the air coming in and continuing the combustion reaction. Halons also have relatively labile bonds. So when the energy from the fire is used to continue the combustion process, if some of that energy is absorbed in breaking these bonds to produce these radicals, heat energy is used up to break these bonds, so it's not as available to continue the combustion reaction. So this is similar. So it has some of the great features that carbon dioxide and argon has. It has some of the great features that water has, in that it can absorb energy. It's absorbing energy and breaking these covalent bonds. And then as a third bonus benefit, once these bonds break to produce radicals, those radicals can start joining up with carbon radicals and oxygen radicals and hydrogen radicals that would normally form during combustion. So instead of the carbon and hydrogen forming bonds with oxygen and releasing a lot of energy, we form less stable bonds, so they really don't release much energy. And that means that there's less energy around to continue the combustion reaction. So you definitely would be familiar with those 3 in case I ask you a question about that. Some of these halons, though, are a problem, because if they're a gas and they eventually do float up into the upper atmosphere, and then they break up due to light from the sun producing radicals, they could mess around with the ozone layer and interfere with that cycle, the ozone cycle. So some more recent halons, or I should say an alternative to a halon, this FM200, has all the same benefits of the halons, but it's an alternative that doesn't go into the upper atmosphere and produce free radicals up there that would react with oxygen and disturb the ozone cycle. So that's another benefit of that particular structure. One more topic that sometimes I ask questions about on exams that you want to be familiar with is autooxidation. Autooxidation is a slow process where a molecule reacts with oxygen. So this typically involves a hydrogen abstraction from an oxygen molecule. Right, so what we said last time was normally we think of oxygen as existing as O2, and that's how almost every oxygen molecule exists on Earth. But if a little bit of energy from the sun, could be light energy or heat, breaks that pi bond, it can produce a diradical. So those pi electrons would split up evenly, and that would have two radicals, a diradical. Each oxygen has a radical, and that can abstract a hydrogen. So if I have a molecule, like cumene, for example, that can produce a relatively stable carbon radical, which I have here, not only is it tertiary and stabilized through hyperconjugation, it's also stabilized through resonance with the ring, the pi bonds in the ring. This could happen sometimes. And then that radical can then react with oxygen, whether it reacts with O2 or the diradical form, it can form a bond with oxygen. And then that oxygen can then pick off another hydrogen, and that can start a chain reaction. So eventually I'll end up with this peroxide in here. Peroxides can be explosive, so that's dangerous. If my molecules are sitting around, if I'm storing them for a long period of time, and they start reacting with oxygen, it can produce explosive peroxides. So I want to avoid that. So I want to talk a little bit about how autooxidation works and how to avoid it, because most of the time it's destructive to molecules that we want to keep intact or store in some way. So this is a relatively slow process because most oxygen molecules don't exist in this form, and when they do form in this way, they usually just come back together to form O2, but once in a while it will collide and start this chain reaction off. And since it's a chain reaction, as the reaction occurs, this radical can then pick off another hydrogen and start another radical here, and then that can react with oxygen, etc. It can go in a cycle over and over again. So we really need to avoid it altogether or try to cut it short once it starts, because once it starts, if it goes out of control, then a lot of these molecules can be converted into this unstable product in a way that we can't reverse very easily. So here is the mechanism that we just mentioned. The diradical or some other radical that might be around will abstract a hydrogen, producing a carbon radical. That can either couple with an oxygen, diradical, or you could think of basically the same thing occurring if it comes in and opens up the pi bond. That would give me the same product either way, so that mechanism could be drawn in either fashion. And then that would abstract another hydrogen and regenerate the radical here. And so this is another example of the correct definition of these terms: initiation, propagation, and termination. Right? So when we used the correct definition, we said propagation is a sum of a series of steps that produce the overall net reaction together, or the sum of the propagation steps have to give the overall net reaction. Early on, we said a lot of times people think of propagation as any step where the radical starts at one location and ends in another location. But that's not necessarily true. So this is an example where this step maybe looks like a propagation step because there isn't a radical already there, and then it ends up on a different atom. But this step here is actually part of the initiation because the propagation steps exclusively are steps when added together give the net overall reaction. So let's look at that. So if I take these two steps and I add them together, so this is the same two steps we just saw, and then I cancel anything that appears exactly the same on both sides, I get the overall net reaction. Oxygen reacting with the hydrocarbon, producing this peroxide. And that's what's left over at the end of the reaction. So these two steps of the mechanism have to be the propagation steps, because adding them together and canceling anything that appears on both sides of the arrow gives the overall net reaction that's occurring. So make sure you're able to draw that mechanism and label the steps correctly if necessary. So how do we avoid this process? It's a relatively slow process, but we can make it even slower. One way is to use dark containers, because often the process starts when light opens up the oxygen bond or produces some other homolytic cleavage that produces some free radicals. So using brown containers or like a plastic container, something that light can't penetrate, really is useful, especially when storing things like vitamins that are susceptible to autooxidation, or even like oils. If you buy olive oil at the store, if you buy it in a clear like glass, like a regular glass container, and you store it for a long time, it might start to go bad, versus if you store it in a brown or colored container, it will last a lot longer. Yeah, we already said this. So this is another key point. If you have a compound that has allylic or benzylic hydrogens, it's especially susceptible to autooxidation, right? We said that back here, because this hydrogen abstraction produces such a relatively stable free radical, it makes the process happen more often. It doesn't take a really high energy transition state to get through the process. And that means that triglycerides are susceptible to autooxidation. Triglycerides are a type of fatty acid that you need in your diet to be healthy. So what triglycerides have are these long carbon chains connected to these ester groups, connected to a glycerol molecule, and these occur naturally in a lot of different foods. There are trans fats and there are saturated fats. These are different types of triglycerides. So the most readily spoiled or oxidized triglycerides are the ones that have pi bonds. And so that's why saturated fats were developed by the food industry, in part because they have a longer storage life. Right? So these are sites of unsaturation. If I get rid of this pi bond and I put hydrogens here instead, then autooxidation is a lot less likely to occur, because if an oxygen radical or diradical were to abstract one of these hydrogens, it would produce a secondary free radical that wouldn't be that stable. So it would be going through a pretty high energy transition state. It wouldn't happen very often. So these things have a long storage life. But the fatty acids that have an alkene group are a little bit more healthy, it seems. They don't seem to correlate with certain heart conditions. But they don't have a very long storage life. And the reason for that is because of the allylic positions. So this hydrogen here is allylic to the pi bond. This hydrogen here is allylic to the pi bond. And those allylic hydrogens are especially susceptible to autooxidation, right? And the reason for that is because when the oxygen radical abstracts that hydrogen, the electron that stays behind can be stabilized by resonance. So it's definitely not going to abstract the vinyl hydrogen or some other hydrogen somewhere along the way. When it can abstract one that produces a resonance stabilized free radical, it's going to go through a much lower energy transition state and happen a lot more often. And that causes the food that maybe contains this molecule to become rancid. So any allylic position that undergoes this reaction where a hydrogen is abstracted to leave a radical, and then the radical combines with another oxygen, is going to end up putting this peroxide structure. And if you eat that, it's reactive and it can start causing other reactions. It's not a good thing to eat. So if you have foods, you want to store them in the refrigerator, obviously. It's a lower temperature, means that there aren't strong enough collisions to undergo a lot of these reactions, so it's much slower at lower temperatures. You want to store things in sealed containers that are don't have a lot of oxygen coming in and out to provide more collisions, or in like brown or dark containers, so the light that won't create radicals that would start this process off. And because the process is a chain reaction, it can get out of control once it starts and really move throughout the material and spoil a lot of the food. One other random question. Why is there a thing called a trans fat, and do you know why they're so bad? Yeah, so this is a cis double bond, right? Because you have two identical groups on the same side of the double bond. This is a trans double bond. You have two identical groups on opposite sides of the double bond. Trans fats, in processed food, trans fats just form more readily. So I don't think it was necessarily the intention of the food industry to create trans fats, but because the cis double bond involves some of these more sterically hindered groups getting a little close together and creating some steric hindrance, those form in nature in certain foods, plants and animals. They use them usually in their cell walls or cell membranes and things like that, but they're not very stable. So I think the food industry, when it's creating artificial versions of these types of molecules, more often will form the trans version because the large groups aren't close together. They don't create as much sterics. The reason that trans fats are not as healthy, I think, I'm correct about this, I'm not 100% sure, but I think it's because of the way the chains are long and straight, right? So if I think about the geometry of this chain, the zigzag here and the pi bond and the angles, it makes this zigzag kind of like long and rigid and extended. When you have a cis pi bond there, you can see in order to make this look extended, the angles here are a little distorted. So really, if you have a cis pi bond, you end up with a situation where it creates kind of like a bend in the chain. And so the cis, the way it bends the chain, it prevents these things from stacking in an organized way right on top of one another. So if I have a bunch of trans fats, and obviously these are mostly nonpolar, they're not going to dissolve well. If I have a lot of that in my blood, these molecules are rigid and they're straight. They can all start to line up next to one another through London forces, and that can clog up my arteries. But if they have more of a bend, then one molecule can't really stack next to the neighboring molecules and form as effective London forces. So they're not nearly as likely to stack together and form deposits that would clog up your arteries. That's the understanding that I have, although I would consult with a medical professional, cardiologist or something to be more certain about that. Either way, we want to avoid the autooxidation there. So another way to, thanks Jose, another way to avoid autooxidation is to use a preservative. So if you have food that you know you need to store for a while because there's a pandemic and you're creating a bunker just in case everyone goes crazy, you would want there to be preservatives in that food. That way, if this reaction started and some free radicals formed, your preservatives would capture those free radicals. And so instead of getting these unstable groups on a carbon, if a free radical formed here, the preservative, I'll just use PRE for preservative, would have a hydrogen that's a sacrificial hydrogen. So that R group or that carbon free radical would pick up the hydrogen instead of reacting with oxygen. And when the hydrogen goes back on there, it reforms the molecule in its original natural nutritious state. So the idea with preservatives is preservatives have a sacrificial hydrogen that they can donate to the fatty acid if the fatty acid starts to form into a radical. So if I have an alkene here, and I'm looking at the allylic position and a radical forms there, the radical can abstract the hydrogen from the preservative, and the resulting radical here will be stabilized through resonance, and there's lots of sterics. So the idea here is it sacrifices the hydrogen to reinstall the hydrogen here, converting the structure back into its original nutritious form, and the preservative then keeps the radical and stabilizes it. It doesn't have to do anything from that point because the radical on the oxygen can be stabilized also on these carbons through resonance, and because there's these big sterically groups here, steric hindering groups, preventing anything from really coming in there and reacting with the radical due to the steric hindrance. These molecules are pretty good at stabilizing radicals, and that's why they're used as food preservatives. Some natural so this basically just shows what I just said. So some natural food preservatives include vitamin C and vitamin E. Vitamin C has a lot of areas of large partial charge. This is a polar molecule. It exists mostly in the hydrophilic tissues, like in your blood and in your cytosol, where there's mostly water as the solvent. But vitamin C has two sacrificial hydrogens. So if any oxidated oxygen or other free radical that could start to do damage to your tissues is around in those tissues, instead of reacting with important molecules that allow your body to function properly, it can react with the vitamin C by abstracting a hydrogen, and the other electron from this bond would stay on, actually would move in here and join up with this electron. And if that also happens on the other side, one electron would come out here, and the other electron would move in here and join up with one here. So that would convert these two CO single bonds into double bonds. And that's the oxidized version of vitamin C. So vitamin C is important specifically because it protects your body from free radicals. It sacrifices hydrogens so that you don't have a bunch of unstable free radicals floating around, doing damage to important tissues. Vitamin E has the same thing, a sacrificial hydrogen. Obviously, it has a big nonpolar group. So vitamin E is produced in your body and remains in fattier areas that where there isn't water as the solvent. So inside your cell membranes and things like that, it protects those tissues from oxidation by sacrificing a hydrogen when necessary. And when an electron stays behind as a radical, it's stabilized through resonance and blocked by sterics a little bit. So it just kind of can then be able to hold that radical without undergoing any deleterious reactions at subsequent. And that's basically the end of the informational stuff. So make sure you understand some of this stuff conceptually. So from what we talked about today, in the beginning, there's a lot of stuff we talked about in terms of drawing mechanisms and predicting reaction outcomes. But there's also some basic conceptual stuff that you might be asked a conceptual question about. You want to at least be familiar with the concepts there and some of the important details we talked about today that I pointed out. For Monday, here are some of the practice questions from the end of the chapter, and some of them I think are in the middle of the chapter. You should definitely practice those. Check your answers with the solutions guide. Let me know if you have any questions. If you want to see any of these worked out on Monday in lecture, try to let me know at least 30 minutes beforehand, and I'll cut and paste the question and put it into a PowerPoint slide so we can incorporate that in the lecture. And then in lecture on Monday, we're going to finish chapter 11 and get into the first bit of chapter 12. So we'll talk a little bit about some more radical stuff, and then synthesis. So we'll do some, we'll use some of these new radical reactions in conjunction with some of the reactions we talked about last semester to try to put together some syntheses and look at some synthesis problems where you're making some structures from simpler, smaller precursors. And that is definitely worth reviewing some of the reactions we did last semester, the substitution, elimination, addition reactions, and there were a number of those. So you want to, the more familiar you are with those moving into chapter 12 next week, the more successful you'll be when trying to complete some of those synthesis problems. So, any questions about anything we talked about today?